Today, my seminar topic is the corona in overhead transmission lines. So the concept of corona in overhead transmission lines. So now in the overhead transmission lines, we might have come across this concept so many times. Okay, so what is a corona in overhead transmission lines? So whenever the transmission line is there, so that overhead transmission line is generally laid in the air, open air. So in the air, so many free electrons are there due to radioactivity in general at any time. So the free electrons are there in the atmosphere around the power conductors. So if power conductors are operating the less than 220 kV, then no problem. If the conductors are operating at greater than 220 kV, then the electric field intensity at the surface of the conductor is such that because of that electric field intensity, this electrons mobility will increase. So what happens, this electron mobility will increase and collide with air molecules nearer to that electrons, so that which causes releasing of some more free electrons in the air molecules. So this process continues. Okay, so and which causes an electron avalanche in between the conductors, and which forms a formation of arc like this. So this is treated as a corona. Okay, so and this can be treated as an LL fault, line to line fault. So the corona can be observed. Okay, so the while you are seeing, you can observe that there is a corona formation in between the power conductor. So how you can detect that? When corona forms, there is a violent glow, and there is a hissing noise, and there is a production of ozone gas around the conductors. So this is about corona formation. Okay, so in order to reduce the corona, the D by R ratio must be greater than 15. So D by R means distance between the two conductors, and R is the radius of the conductor. So it must be greater than 15 throughout the length of the conductor. But the transmission lines are laid at so much distance. They are running at so much distance. So it is difficult to meet this condition. So at anywhere there is a chances of formation of corona. So when corona is formed, corona is initiated, so the corresponding voltage is called as disruptive critical voltage, VD. Okay, so disruptive critical voltage. So this is the voltage at which the corona is formed. So its value is G0 delta M or ln D by R. So G0 delta M R ln D by R. So for single phase, it is in kilovolts. Okay, So where G naught is the dielectric strength of the air. So the G naught is dielectric strength of the air. Its value is 21.2 kV. That is the RMS value. And delta is called as air density factor. Air density factor. And so it is given by 3.92 B by 273 plus T, where B is the atmospheric pressure and T is the temperature, atmospheric temperature. So, and D is the small d is the distance between two conductors. So distance between two conductors, and R is the radius of the conductor. So this is the disruptive critical voltage. The voltage at which the corona is initiated is called as disruptive critical voltage, and M is the surface irregularity factor. Surface irregularity factor. Surface irregularity factor. So it depends upon the surface of the conductor. For normal conductor, it is one value, and for normal conductors, it is one value, and for bundle conductors, it is some value. Okay. So this is the disruptive critical voltage. That means the voltage at which the corona is initiating is called as disruptive critical voltage. And one more voltage that is called as visual critical voltage. So it is given as G naught M V del R into 1 plus 0.3 by square root delta into R into ln d by R. So that means this is the voltage at which you can visualize the corona. So that's why this is called as visual critical voltage. So again, G naught value is 21.1, MV is surface irregularity factor, delta is 3.92 B by 273 plus T, R is the radius of the conductor. So you see the difference between disruptive critical voltage and visual critical voltage is, so it is visual critical voltage is 1 plus 0.3 by square root del R times the disruptive critical voltage. So this times is required to visualize the corona. So now you see the main problem with the corona is, so when corona comes when corona appears at the overhead transmission lines, this corresponds to a loss that is called as a corona loss. So whenever corona occurs, there is a loss in the overhead transmission line that is called as a corona loss. So it is given as 244 into 10 power minus 5 into F plus 25 by del square root R by D into Vp minus Vd whole square. So this is in kilowatt per kilometer per phase. So whenever corona occurs, there is a loss corresponds to corona, that is called as corona loss, that is 244 into 10 power minus 5 F plus 25 by del into square root R by D into Vp minus Vd whole square, where Vp is operating phase voltage, Vd is the disruptor critical voltage, F is the operating frequency, and R is the radius of the conductor, D is the distance between the conductors, delta is the air density factor. Okay, so now whenever the corona loss occurs, it depends upon so many factors. The corona loss is dependent on so many factors. So the factors which are affecting the corona loss is, one is electrical factors. So electrical factors. Second one is atmospheric factors. Atmospheric factors. And third one is the factors related to size of the conductor. Size of the conductors. So these are the various factors which are associated with the corona loss. So corona loss depends upon all the three factors. So what are the electrical factors? So you see, the corona loss depends upon, by seeing this expression, the corona loss depends upon frequency, operating frequency. So it depends upon operating frequency. So if frequency is high, the corona loss is high. If frequency is less, corona loss is less. So that means when you compare the 50 Hz and 60 Hz frequencies, so when compared to 60 Hz frequency, in 50 Hz frequency, the corona loss is less. So, and if you see in the DC, because the frequency is 0 Hz, so corona loss is very less when compared to AC. So that's why in HVDC transmission, the corona loss is very less. Nowadays, HVDC transmission is preferred because of its so many advantages. So one of the advantages, corona loss is very less. So, and the frequency also depends upon the waveform, supply waveform. So if it is sinusoidal, then there is no problem. Suppose if it is distorted like this, so it contains of so many harmonics. So third harmonic, fifth harmonic, like this. Third harmonic frequency three times the fundamental frequency, fifth harmonic 5 times the fundamental frequency. Like that, when supply voltage is distorted, supply voltage waveform is distorted, then the frequency of the supply increases. So because of that one, the corona loss also increases. So in that way, it depends upon electrical factors. And the second one is atmospheric factors. So it is based on atmosphere. So that means if you compare in the normal areas and hilly areas, in the hilly areas, the corona loss is very high, because in the hilly areas, the corona loss is very high because it depends upon air density factor delta. So that is 3.92 B by 273 plus T. So in the hilly areas, the temperature is less, but the atmospheric pressure is very, very less when compared to temperature. It is predominating the temperature. That's why the air density factor is less. Whenever air density factor is less, the disruptive critical voltage that is proportional to air density factor is less. So whenever disruptive critical voltage is less, the power loss is proportional to Vp minus Vd whole square. So when air density factor is less, Vd is less. So at less voltages, the corona is taking place. So if operating phase voltage is constant, at very less voltages, the corona is being occurred. So when this Vd is less, the power loss is very high. So that's why when compared to normal areas, in hilly areas, the corona loss is very high. And the third one is factors related to size of the conductor. So whenever the size of the conductor is more, so that means if its radius is very high, so if its radius is very high, so disruptive critical voltage that is proportional to radius of the conductor, so it is also very high. That means that the corona occurs at high disruptive critical voltage. So when disruptive critical voltage is very high, the power loss that is proportional to Vp minus Vd whole square. So when this Vd is high, the power loss is less. So whenever the size of the conductor increases, the corona loss decreases. So these are the various factors associated with the corona loss and how to reduce the corona loss. So reducing corona loss. What are the methods to reduce corona loss? So already we have discussed, that is larger diameter of conductors, larger diameter of conductors. Second one, by using bundle conductors. And third one is using hollow conductors. Using hollow conductors. So these are the various ways to reduce the corona loss. So this all about corona. Thank you.